All right, guys, welcome to your video today. This is going to be a continuation of what we did last time on differential equations, so taking it a step further into some more AP-style problems, and you're actually going to learn your first BC topic today, so that's actually pretty exciting as well. So we're going to start off with the crazy potato problem of 2017, and really the reason I call it the crazy potato problem is because you'll notice as we go through this problem, the phrase, the internal temperature of the potato, shows up, I think, about 7 times in this problem. So the wording is really just a lot in this question. So you can just kind of see a couple of times here, even in the header of the question, it shows up several times, and it'll actually show up even in the questions themselves. So you've got to be careful and not get bogged down in all of the wording and try to actually figure out what are they asking me to do with the calculus. Okay, so we are given a differential equation here. That differential equation is dH dt is equal to negative 1/4 times h minus 27. And so we're going to be working with that differential equation in part A and part B. And then in part C, they're going to throw a completely different differential equation at us. So without further ado, let's go ahead and jump in here to part A. It says, write an equation for the line tangent to the graph of h at t equals 0, and then use that equation to approximate the internal temperature of the potato at time t is equal to 3. So if I go back to that first sentence, it says write an equation for a tangent line. I know how to do that. And so even though the wording seems really crazy, I know that in order to write the equation of a tangent line, I need a point and I need a slope. And so I need a point at t is equal to 0 on the graph of h of t. And that is given right here with the initial condition, h of 0 is equal to 91. So there's my point. To find my slope, I'm going to go into my derivative. And so my derivative is right here, dH dt. And so I'm just going to plug 0 and 91 into that equation. So dH over dt evaluated at 0 to 91. Okay, now you got to be careful because the only variable that's in that differential equation is actually h. So I'm not actually going to plug 0 in anywhere. I'm just going to be plugging 91 in for h. And if you calculate that, you're going to get a slope of negative 16. Okay, so that means my equation for my tangent line is going to be y is equal to my y value, which is 91, plus my slope, so minus 16, multiplied by t minus 0. And I'm just using t because I know that that's what the independent variable is here. Instead of using x, this problem is using t. Okay, so now if I want to figure out what h of 3 is, I just need to plug 3 in to my tangent line. So 91 minus 16 multiplied by 3 minus 0. And you could calculate that if you want to, but this is a free response question, so there's no necessity to do that. You can just leave this as your final answer. Okay, in part B, it says to use the second derivative of h with respect to time to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time 3. So the question is, how in the world am I going to use a second derivative to determine if my answer in part A is an under or an overestimate? And here's the answer. I know that second derivatives tell me about concavity. And so what do I know about concavity? I know that if a function is concave up, that means that the tangent lines are below that function. And similarly, if a function is concave down, I know that the tangent lines are above, which means that if it's concave down, that the estimates are going to be overestimates. And then if it's concave up, like it is in this picture, then the estimates are going to be underestimates. And so we're going to use the second derivative to help determine the concavity of h so that we can figure out if the tangent line is going to be an over or an under approximation. Okay, so going back up and looking at our dH dt, we need to take the derivative of that here in part B. And so the second derivative of h with respect to time is going to equal to negative 1/4 is just a constant, so it's going to hang out in the front. And I'm going to multiply by the derivative of h minus 27 with respect to t. That's the key ingredient there, that the derivative is with respect to t, which means that's going to be dH over dt. Now, I know what dH dt is, so I'm going to substitute it in here, negative 1/4 times h minus 27. And if I simplify this, multiply the negative 1/4 together, that's going to give me positive 1 over 16 times h minus 27. Okay, so if I'm trying to find concavity, I need to know, is this second derivative positive or negative? And that really depends in this case on h, since that's the only variable. So if you go back up to the header of the question, there's this little phrase here, and I'm going to highlight it in blue, that says the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. So what that means is that this h right here is always bigger than 27, which means h minus 27 is always bigger than 0. So I can say that this second derivative is always positive. And so now follow the line of thinking here. If the second derivative is positive, the graph of h is concave up, and concave up, by drawing a little picture here, means that the tangent lines are below, which means that the answer will be an underestimate. So I'm going to write a sentence here that says all of that. H is concave up. That's the conclusion that can be made from the second derivative being positive. So our answer in part A, since the graph is concave up, it must be an underestimate. Okay, so letter C now is going to throw a different differential equation at us. It says for t greater than 10, an alternate model for the internal temperature of the potato is the function g that satisfies this differential equation, where g is measured in degrees Celsius and g of 0 is equal to 91. So once again, there's my initial condition. And this time the question is asking us to find an expression for g of t. Okay, well that is just fancy language, or maybe not fancy language, for find the particular solution to the differential equation. So this is where I'm going to bring out my process of separating variables and finding antiderivatives and putting plus c, and then using the initial condition to find c, and then finally solving, in this case, for the variable g, because notice that g is taking the place of the variable y, and t is taking the place of the variable x. So when I separate the variables, I want all of the t's to be on the right side of the equation, so I'm going to multiply by dt. I'm also going to leave the negative over there because it's a constant. And then I'm going to have to divide both sides by g minus 27 to the 2/3. So dg over g minus 27 to the 2/3 power. Okay, that is a successful separation. So now I'm going to take the antiderivative of both sides. The antiderivative of the left side is really easy, negative t plus c. Okay, so you can think about this as being like the antiderivative of negative 1 with respect to t if you want. And then for the other side, I've got to move this g minus 27 to the 2/3 up to the numerator. So that's really going to become g minus 27. I'm going to try to write it in this space right here. G minus 27 to the negative 2/3. And so when I bump up and divide that, it's going to become g minus 27 to the positive 1/3, and then divided by 1/3 is really the same thing as times 3. Okay, so there's my antiderivative of the left-hand side. Now I'm going to use the initial condition, which was g of 0 is equal to 91. So 91 is going to go in for g, minus 27 to the 1/3 is equal to negative 0 plus c. And so c is going to equal to that number, which if you calculate it, you're going to get 3 times 64 to the 1/3. 64 to the 1/3 is 4, so 3 times 4 is 12. Okay, and so I'm going to come back to that line where I first had my c, so 3g minus 27 to the 1/3 is going to equal to negative t plus 12 now, and I'm going to try to solve for g. So the first thing is to divide by 3. So g minus 27 to the 1/3 is going to equal to negative 1/3 t plus 12 divided by 3 is 4. The next thing is to get rid of the 1/3, so that would be to cube both sides. So I'm going to put all of this in parentheses and then cube it. And then the final thing to get g by itself will be to add 27. So g is going to equal to 27 plus negative 1/3 t plus 4 to the third power. Now, I'm not quite done here because there's one last final thing that they're wanting me to do. They're saying, based on that model, what is the internal temperature of the potato at time 3? And so all that really means I need to do is evaluate this g at t is equal to 3. So g of 3 is going to equal to 27 plus negative 1/3 times 3 plus 4 cubed. And since it's free response, you're more than welcome to leave your answer just like that. Okay, on the next problem, this is from 2015, BC number 4. This is a little bit of a different problem because this equation, 2x minus y, is actually not separable. And so from time to time, they'll give you equations that are not separable. If they're not separable, what that means is they'll never ask you to solve the equation. Okay, so they're going to ask us to do some other things here, but solving the equation is not one of them. In letter A, they want us to sketch a slope field. So sketch a slope field for the given differential equation at the 6 points indicated. I'm going to create a little chart here to help myself stay organized. Okay, so the first point that I come to, and really you can do these in whatever order that you want. If I look at this point, that's the point 0, 2. So if I put that on my chart and I plug 0, 2 into the differential equation, 2 times 0 minus 2 is going to give me negative 2. So again, I'm plugging back into this right here. I get a slope of negative 2. So at that point, I'm going to do my best to put a line segment that has a slope of negative 2. Okay, the next point that we could do is 0, 1. That's going to give me a slope of negative 1 by plugging into dy dx. And so negative 1 will be a slope that looks something like this. Okay, didn't mean to change colors on you there, but you get the point. I'll go back to black here. Okay, and then what about 0, negative 1? So that would be this point down here at the bottom. 0, negative 1 is going to give me a slope of 1. So I'm going to do my best to draw a line segment that has a slope of 1 there. Okay, keep going. So if I do, how about 1, 2? Okay, so 1, 2, if I plug that into 2x minus y, I believe that's going to give me a slope of 0. So I'm going to have a slope of 0 there. Okay, at 1, 1, I believe that's also going to give me a slope of 1. You can double check that for yourself. So there's my slope of 1. And then finally at the point 1, negative 1, that's the last point that I haven't done yet. 1, negative 1 is going to give us a slope of 3. And so that'll be my steepest line yet at that point. Okay, just as a reminder, they're not looking for any sort of a table. That's really just more for you to keep yourself organized and to help yourself out. They're going to be grading just your line segments. Okay, letter B, find the second derivative of y with respect to x in terms of x and y. So just for reference, dy over dx was equal to 2x minus y. And so the second derivative of y with respect to x, remember, we're taking the derivative with respect to x, so the derivative of 2x would be 2, and the derivative of y with respect to x would be dy over dx. Now, it wants the answer in terms of x and y, so that means I've actually got to replace dy dx with what it is, and so I get 2 minus 2x minus y, which if I go ahead and distribute the negative is going to give me 2 minus 2x plus y. Okay, then determine the concavity of all solution curves for the given differential equation in quadrant 2. So the question is, what's special about quadrant 2? Well, in quadrant 2, what I know is that x is negative and y is positive. And so if I were to plug a negative in for this x, which is what I would do in quadrant 2, this term is going to go back to positive because it would end up being a minus a negative. And then if I were to plug a positive y in right here, that would obviously be positive. So what I would have is that I would have a positive 2 plus something plus something. And so no matter what, in quadrant 2, this is always going to be positive. And so if the second derivative is positive, what we can say about all the solution curves is that they are concave up, since the second derivative is positive. So all solution curves in quadrant 2 are concave up, since the second derivative of y with respect to x is positive. All right. Letter C, let y equals f of x be the particular solution to the differential equation with initial condition f of 2 is equal to 3. Now that's normally the language that we hear when we want to solve the differential equation. But remember, I told you we can't solve this one because it's not separable. So they're going to ask us to do something different here. It says, does f have a relative min, max, or neither at x is equal to 2? Justify your answer. So what we're going to do here is we're going to use the second derivative test, because we have the first derivative. The first derivative, remember, was equal to 2x minus y, and we found the second derivative in part B. So we're going to use that if necessary. So I'm going to evaluate this at the point they're talking about, which is 2, 3. And so if I plug that in, I'm going to get 2 times 2 minus 3, which is equal to 4 minus 3, which is equal to 1. Now, let's pause here for a minute. If the first derivative equals to 1, this is not even a critical point. F of 2 is equal to 3 is not even a critical point because the derivative does not equal to 0. So if 2, 3 is not a critical point, it cannot be a max or a min. So the answer here is going to be neither. It can't be a max or a min because dy over dx, the derivative at 2, 3, does not equal to 0. Okay, so if you're not a critical point, you can't be a max or a min. So when we plug into the first derivative and we get anything other than 0, we know that it can't be a max or a min, so it has to be neither. Okay, part D is a little goofy. I'm going to show you the easy way to do this. It sounds really difficult. It turns out that it's not real hard. Okay, so find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So if it is a solution to the differential equation, it can be plugged into dy dx equals 2x minus y and work. And it can also be plugged into the second derivative and work. So let's take a look at this. Y equals to mx plus b. So that means that y prime, or dy dx, if you want to think about it like that, is going to equal to m. And that means that y double prime, which is the second derivative of y with respect to x, is going to equal to the derivative of m. Well, m is just a constant, so that's going to equal to 0. And so now what do I have? Well, this right here from part 2 was 2 minus 2x plus y is equal to 0. And so now if I solve for y, I'm going to get y is equal to positive 2x minus 2. And so right there, that tells me what my m and my b are. M is that coefficient on x, which is going to be 2, and b is the y-intercept, which is negative 2. Okay, so I hope you didn't hurt your head too much on part D. Like I said, not quite as hard as it looked or as it sounded, and hopefully my explanation makes a little bit of sense. Okay, this example from 2013 is going to introduce us to 2 new concepts, both of which are very important. And so I'm going to introduce you to a new thing in letter A, and then in letter B, we're going to do something else that's new. And then part C will be our typical solve a differential equation. So in part A, it says to find the limit as x approaches 0 of f of x plus 1 divided by sine x, and show the work that leads to your answer. Now, typically what we try to do when we find limits is we just try to plug in what x is approaching. So in this case, x is approaching 0. So if I plugged in 0 to that function, I would get f of 0 plus 1. And I'm going to do this as scratch work way up here. Okay, f of 0 plus 1. And so what is f of 0? Well, the question says that f of 0 is equal to negative 1. So this will be negative 1 plus 1 which is equal to 0. So the numerator is going to be 0. What about the denominator? Well, the denominator is going to say sine of 0, and that's also going to equal to 0. So this limit, listen to my words carefully, is going to be of the form 0 over 0. I didn't say it equals to 0 over 0 because a limit cannot equal to 0 over 0. It is of the form 0 over 0. And so whenever a limit is of that form, 0 over 0, we have a rule that will allow us to try and find what the value of that limit is. And that rule is called, are you ready for this? L'Hopital's rule. And I know you just busted out laughing because you thought I was going to say El Hospital. That's how it's spelled, but the way that it's said is L'Hopital's rule. Okay, and here's what L'Hopital's rule says. I'm going to write out what it says word for word. So if limit as x approaches a of f of x divided by g of x is of the form. So notice I didn't write equals. I said is of the form 0 over 0, or it turns out infinity over infinity. So if either of those two forms is what the limit is, then what we can do to find the limit is the following. The limit as x approaches a of f of x divided by g of x is going to be nothing more than, and I hope I can do this without running out of the screen, limit as x approaches a of f prime of x divided by g prime of x. And so I want to point out something important about this. First of all, never write that a limit equals 0 over 0. I'm going to show you exactly here in Part A how to write this out on the AP exam so that we do not lose credit. So that's the first thing. Do not write equals 0 over 0. The second thing is, notice here that we're taking a derivative and there's a quotient involved, but we didn't use quotient rule. It's just the derivative of the top divided by the derivative of the bottom. Okay, so it's not quotient rule, derivative of top divided by the derivative of the bottom. That's it. Here is how we're going to write the answer to obtain full credit. I already know that the numerator and the denominator are both going to 0, but I need to clearly say that for the reader. So I'm going to say the limit as x goes to 0 of just the numerator, f of x plus 1, is equal to negative 1 plus 1, which is equal to 0. Furthermore, the limit as x approaches 0 of just the denominator, sine of x, is also equal to 0, because when I plug in 0 to the sine of x, I get 0. Therefore, by L'Hopital's rule, and you don't have to be a perfect speller, but really it's not that hard to spell, El Hospitals is what it looks like, even though it's called L'Hopital's. L'Hopital's rule, what we can say is that the limit as x approaches 0 of f of x plus 1 divided by sine x is equal to the limit as x approaches 0, and the derivative of the numerator is going to be f prime of x, and the derivative of the denominator will be cosine of x. Okay, what I'm going to try to do now is plug 0 in again. So now I need to figure out how to find f prime of 0, and f prime of 0 is going to be found by using the differential equation. So if you want to come over here and do some scratch work and evaluate that differential equation, when x is equal to 0, I know that y is 1, negative 1. So let me erase that and try that again. 0, negative 1 is the initial condition. And so what is that going to give me? It's going to give me negative 1 squared times 2 times 0 plus 2. And so that will equal to 2. And so that numerator is going to equal to 2. And then cosine of 0 is going to be 1. And so the answer here is going to be 2. Okay, so L'Hopital's rule, if the limit is of the form 0 over 0 or infinity over infinity, then we can say that the original limit is equal to the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. And we will do this a lot more as we go on throughout the year. Okay, I'm going to skip part B for now. I'm going to come back to it because I'm going to do another example separate of this one and then come back and do letter B with you when we talk about Euler's method. Yes, I said Euler's. It looks like Euler's. I understand that. It's pronounced Euler's, so if you want to sound like you know what you're talking about, say Euler's. Don't say, Euler's, not Euler's. Euler's is not correct. Okay, so in letter C, find y equals f of x, the particular solution to the differential equation with initial condition f of 0 is equal to -1. So I'm going to write down my differential equation just for reference so I have it in front of me. Y squared times 2x plus 2. Okay, so if I separate the variables, I'm going to multiply both sides by dx. So that will give me 2x plus 2 times dx over here. And divide both sides by y squared. When I do that, it's going to end up being y to the -2 power dy, because it would have been in the denominator, but I need to move it up to the numerator so that I can take the antiderivative. Okay, so the antiderivative of y to the -2, increase the exponent by 1, it becomes -1, so 1 over y is what we'll get. And then if you divide by -1, you're going to get a negative. So -1 over y will be the antiderivative there. And then the antiderivative of the right-hand side will be x squared plus 2x plus c. Okay, at that point, we want to use our initial condition over here in order to figure out what c is. So -1 over -1 is going to equal to 0 squared plus 2 times 0 plus c. And so that means that c is going to equal to 1. And so back up here, I'm going to have -1 over y is equal to x squared plus 2x plus 1. Okay, and in order to get y by itself, in order to finish this, I'm going to change the signs of everything. -x squared minus 2x minus 1, and then take the reciprocal. So y is going to equal to 1 over -x squared minus 2x minus 1. So that will be my final answer there. And that will complete this problem. Again, we'll come back to part B after we do this last example on the last page. Okay, so on the last page, I'm going to introduce Euler's method to you. Euler's method is a way to approximate solutions to differential equations. So whenever we can't solve the differential equation, we can still estimate the solution at particular points using this method called Euler's method. And Euler's method uses tangent lines to approximate these solutions. Okay, so given the differential equation, dy dx is equal to x plus y, let y equals f of x be the particular solution to the differential equation with this initial condition, f of 4 is equal to -1. Use Euler's method starting at x equals 4 with 2 steps of equal size to approximate f of 4.2. Show the work that leads to your answer. So first of all, what we need to do is we need to figure out if we're going to take 2 steps of equal size and we're going to go from x equals 4 until x equals 4.2, how big does each step need to be? Okay, so I'll let you think about it for a second. If we're taking 2 steps and each time we need to go 0.1. Yes, you're right, 0.1. Delta x is going to equal to 0.1. And so that's going to be my delta x. And so here's how this is going to work. I mentioned tangent lines. So look here. I know that for a tangent line, in general, I've got y equals y1 plus m times x minus x1. Now I'm going to give this a little bit of a different notation now. Okay, I'm going to keep y1. That's a good notation there, y1. Instead of m, though, I know m represents slope. So I'm going to change that to dy dx, because that'll represent slope. And then x minus x1, that's like a change in x. And so in order to represent change in x, I'm going to write delta x. And so this is going to be the form of the tangent line that we're going to use in order to answer this question. And so what I have students do is create a very well structured little table here. And so this is how this works. And sometimes they use 3 columns, sometimes they use 4 columns. It doesn't really matter. It kind of just depends on what you want to do. Okay, but here's what we have at the top of our headers. We have x, we have y, we have dy dx, and then the new y coordinate is going to equal to the current y coordinate plus your dy dx multiplied by your delta x. And you've got to make sure that this is labeled correctly, because if you do this on the AP exam and it's not labeled correctly, then it's not going to go well. Okay, so we've got to make sure it's labeled correctly. Okay, we always start at our initial condition. So our initial condition is 4 and -1. I'm going to calculate the slope, dy dx, at that point. So going into my differential equation, it says x plus y, so 4 plus -1 is going to give me a slope of 3. Okay, in order to calculate the new y-coordinate, the new y-coordinate is going to be the current y-coordinate, which is -1, plus the slope, which in this case is 3, multiplied by delta x, which is going to be 0.1. And so this is going to give me a value of -1 plus 0.3, which is -0.7. And that is going to be my new y-coordinate on the next line. My new x-coordinate, since I took a step of 0.1 from 4, my new x-coordinate is going to be 4.1. Okay, and so notice that my delta x here would be 0.1 like it was supposed to be. Okay, now I'm going to do it again. So I'm going to recalculate the slope. So 4.1 is the new x, plus -0.7 is the new y. And so that's going to give me 3.7. And then I'm going to go ahead and calculate what the new y would be. So the new y, according to what this says up here, based on my form of the tangent line, is going to be the current y-coordinate, -0.7, plus my slope of 3.7 multiplied by delta x, which is 0.1. And so you can go ahead and use the calculator there. I'm going to pop my calculator open and just calculate that real quick. Hopefully type it in right. So -0.7 plus 3.7 times 0.1. And I got -0.33. And so that's the new y-coordinate now, -0.33. And my new x-coordinate, after I take another step of 0.1, is going to be 4.2. And so now look what we have here. We have an approximation for f of 4.2, which is what we wanted. F of 4.2 will be approximately -0.33. And so that is Euler's method. It helps us approximate solutions of differential equations using tangent lines. And so now that we know that, we're going to go back to the previous problem and see if we can answer this question, part B. Use Euler's method, starting at x equals 0, with 2 steps of equal size to approximate f of a half. And so the question is, what does delta x need to be if I'm going from 0 to 1/2 in 2 steps? Okay, well, hopefully you said that each step needs to be 1/4. So delta x is going to be 1/4. I'm going to set up my table here. And so it's going to say x, y, dy dx, and then the form of my tangent line will be y plus dy dx multiplied by delta x. Okay, so starting at the initial condition, let's remind ourselves what that was on this problem. It was 0 and -1. And let's also remind ourselves of what dy dx was. I believe it was y squared times 2x plus 2. And so if I plug dy dx, or 0 and -1 into that dy dx, by the way, notice that I already did that in part A. So if you'll look back over here, I actually already did that right here when I was using L'Hopital's rule. So I can just go ahead and cheat here and say that the slope is 2. And so my new y-coordinate is going to be -1, the current y-coordinate, plus the slope, which is 2, times delta x, which is 1/4. And so that's going to be -1 plus 2/4, which will be -1/2. And so my new y-coordinate on my next line will say -1/2, and my new x-coordinate is going to say 1/4 after I take a step of 1/4. Okay, so now we're ready to recalculate the slope at the next point. So 1/4 and -1/2, I'm going to plug those in to my dy dx. So that's going to be -1/2 squared multiplied by 2 times x, which is 1/4, plus 2. And so that's going to give me 1/4. I'm going to calculate this under here. 1/4, and then 2 times 1/4 is a half, plus 2 is going to be 5/2. So this will be a slope of 5 over 8. And so now in my last column, current y-coordinate is negative 1/2 plus my slope of 5/8 multiplied by my delta x, which is 1/4. And so this will be negative 1/2 plus 5 over 32. And so that ends up being negative 11 over 32. Now, since this is free response, obviously you don't have to do all of that arithmetic, okay, but I'm just doing it here basically to check my answer. So now my next step is going to be at x is 1/2. My y-coordinate is negative 11 over 32. And so now I can say that the approximation for f of 1/2 using Euler's method is negative 11 over 32. Okay, hope that was all helpful. If you have any questions, as always, please feel free to